New Year, and welcome to the Ada Lovelace Day podcast. This is our first episode of 2017, and we're welcoming in the new year with a whole new segment. You'll find out more about that later. I'm Sue Charman-Anderson, and this month I'm talking to Professor Elaine Chew about how she uses mathematical and computational models to reveal the hidden structures of music. And I'll be chatting to marine biologist Dr. Helen Scales about the pioneering work of the shark lady, Eugenie Clark. So this month we're talking to Professor Elaine Chew, who is a Professor of Digital Media at Queen Mary University of London. Hi Elaine.
Hi Sue, thank you very much for having me.
It's great to have you on. So I'm kind of curious, what does a Professor of Digital Media do?
Well, I kind of inherited the title because the school advertised for a position for Professor of Digital Media, and I haven't had time yet to change the title. But basically what I do has nothing to do with like news and media. I'm actually a musician and I work on digital music. What I do is I design automatic methods to process music that is normally in digital form, so that can be recorded music, it can be music notation, can be scores, but we try to understand music or create computer algorithms that can do the kinds of things humans can do when we listen to music, like understand what is the most important note, what are the segments, what are the important melodies. We try to learn from what humans do and to encode that kind of knowledge in mathematical terms that can be scientifically examined and investigated.
Wow. That is not at all what perhaps one might expect from the term digital media. How did you end up in this role? Like, how did you become a sort of scientific explorer of music?
Oh, I like that term. Maybe I'll become a professor of scientific explorer of music. I like that. Well, I didn't start off as a scientific explorer of music. I sort of started off into parallel tracks. I was studying music separately from studying mathematical and computational sciences. And that became sort of the two main threads in my life. And somewhere as I got more advanced into my career, I realized that it was getting impossible to still juggle the two of them separately. I was having great difficulty having enough time to do both of them. I discovered at that point that it was possible that there was a new field forming, or rather there was sort of a field that had been percolating and starting out some decades before, but was really growing around the late 90s and around the year 2000, and really burgeoning. And this was a field that combined music and technology. And whenever you combine music and technology, you need mathematical representations, you need computational algorithms to be able to handle music. And music is such an integral activity to the human experience that in order to do this in a way that is meaningful, we have to learn from how humans engage with music. And to me, that was the most interesting part, to be able to use that knowledge about music, the knowledge about how we make music, how we listen to music, and to try to translate that into mathematical and computational terms so that we can use that knowledge in new creative ways.
And how do you see that knowledge being used? What are these creative ways?
Well, as a musician by training, the ways in which we use that is most interesting to me are ways in which we can help all people, because some of this knowledge is very highly specialized. Some of it requires many years of training and a very high level training to be able to appreciate or have the skills to manipulate music in these ways. To me, the most interesting thing is that by using computational tools to, in a sense, in an objective way, make apparent the kinds of things that are being done to music, to shape music, we can make it more readily accessible to just generally any person. who can see these results. So one of the things that we do is we look at ways of representing music in ways that are easily visualized with computers. And if you can visualize these structures, if you can see what is happening in the music, then perhaps that can guide you to actually hear these kinds of structures in the music.
I'm sort of reminded of something a friend of mine said to me just a couple of months ago, that music is just maths you can hear. And you're kind of turning music into maths you can see.
Right, yes, that's a very good way to put it. Well, the cool thing about music is both art as well as science. It's one of those things that straddles both areas, and maybe more so than other artistic fields, music is readily translated into mathematics. It embodies so much of the kinds of artistic exploration that is done in other artistic fields, but provides a medium to express these kinds of explorations and creativity in mathematical terms.
Yeah, there's kind of an analogy that's sort of starting to build in my head a little bit around sort of linguistics, where sort of linguistics is a way to try and understand and communicate the structures of language. It seems that what you're trying to do is find a way to understand and communicate the structures of music. I've taken a few music lessons, and I was never very good at music theory. I found it a little confusing. And you're kind of taking that music theory and expressing it in a mathematical way, in a visual way.
Yes, and I wouldn't say that's your fault. And I think many people struggle with how music is expressed theoretically, because that theory, by and large, has not changed in centuries. And we need to find new ways to actually express what we know about music. And that expression also, the means of expression has changed and advanced greatly over time. Today, with computers and more advanced mathematics, we can do a lot more in expressing what we know about music than we could just even decades ago. And that has not been fully exploited. That was the most wonderful thing about discovering that I could make some contributions in this area, is that there is just so much to do. I could see sort of my whole life mapped out in front of me, and there it was. This is what I want to do for the rest of my life, and maybe I'll get somewhere, and I don't expect I'll finish it, but I hope that more people will continue.
I love that feeling of all that possibility. Can you give us an example of some of the music that you're working with and some of the results that you've got?
One of the earliest things I did was to find a mathematical expression for tonality. And most of the music that we hear is actually tonal. Any music on TV, ads, musicals, popular music, it's pretty much almost all tonal in nature. And that's because we've grown to understand tonal music. And I wouldn't say that's how music has to be, but it's the way that music has developed in much of the cultures that we live in. And different cultures have different ways of structuring their music, but I'll give an example of very old music here. And this is old in that I'm just drawing an example from Bach. And the idea of tonality is that music that is tonal, we immediately get a sense of what is the most stable sound, the most stable pitch. So if I just played this, we know that that has not finished. And at the moment, the context that has been established so far, it is the key of G minor, and the most stable tone so far is. And it's still not finished, but it is going to change context. It's at this moment going to switch from G to B flat. Before it was this, and now it's B flat. And we're going to continue in B flat. And that's B flat, confirming that we are now in B flat. And we're changing now. This is G major, C major, and back to G minor. So by changing the context and varying it causes these feelings of tension. We have a home key that has been established, and then we move to B major, which perhaps sounds happier in a way. So here we are in B flat, and then we start changing back. And to get back to the home key, we go through G major, C minor, and back to G minor. And to G minor, and we are now satisfied that we have reached home. And this is how we tell a story with music. We're able to tell a story because of these kinds of structures. And it's because we understand these structures and how they're expected to move that I can play around with time. I've played around with time when I played that. I did not play that straight. I took lots of time in between to sort of highlight things that were interesting. And the reason I could choose to highlight those things with that much time in various parts of the piece was because of those structures. So the ways in which we make music, we create music, we compose music, we perform music is all tied to these structures.
When you sort of say that, it's not finished, even I kind of have that sense of like, you're expecting it to resolve, right?
Yes, exactly. Right. And that kind of tension. And in a way, I think some people would say that's what makes music sensuous, that kind of expectation and sort of wanting it to be resolved and playing around with that expectation, and whether withholding it or to give it, that is what makes the tension in music, the storytelling in music interesting. And that's what makes us come back to music time and again. And that's what makes different people telling the same story in different ways interesting. Otherwise, we wouldn't come and listen to this piece of music played 200 other times. We come back to it because there are new things to say with it.
And so what have you been doing in terms of your analysis of these structures? How does that work? You're feeding this into a computer and then getting what out of it?
So one of the earliest models I came up with is called the spiral array, and it's a geometric representation for tonal structures. And it shows, using three-dimensional space, things that are far away are sort of perceptually farther apart. And so when you move far away, there's sort of a tension of wanting to come back to the home base if a home base has been established, which was kind of what I was illustrating through sound earlier. But except if you have a mathematical model, and especially if it's 3D and geometric, you can actually see this in a three-dimensional space. And so if you can actually see it, and you can see it moving far away, and you can sense it going far away, and the tension of pulling, the elasticity of pulling far apart and trying to come back, that hopefully will help solidify that kind of help in internalizing the kind of knowledge about how music works.
So who do you think will benefit the most from this work? Are you focused on helping music students, or is there a more sort of general application?
There are many applications. One, of course, pedagogy, music pedagogy is one of them. These are the kinds of things that advanced musicians would be playing around with. But perhaps not everybody knows how it is done. And so if there are visual ways of showing it, it could be integrated into the way music is learned. I guess initially I was able to start in this field primarily because of the rise of music technology for the application of music information retrieval. Music information retrieval is a field where, well, I guess the equivalent would be sort of Google for text. If you're searching for certain text and you write a sentence into Google, it will find you related documents. So imagine sort of a Google for music, and you could sort of have a snippet of music sort of played into it, and it will find you and retrieve all other similar kinds of music. So music can be similar in different ways. So if you are interested in the structures of music, how it evolves over time, if you're interested in finding other pieces of music that evolve harmonically or tonally in the same ways, you would need a mathematical representation of it. And so this would be an application of how it would be used industrially. This has been sort of the driving force behind how the field of music technology has grown so much in the past 15, 20 years. Before the advent of computers and large databases, it was perhaps harder to motivate sort of large-scale interest in this kind of work. I'm not saying that that's right or wrong, but I mean, my main interest really is to find ways in expressing, I mean, the beauty in music, I mean, the possibilities in music in as many ways as possible, so that more people can actually appreciate what it is that goes into it. What I hope to be able to contribute most to is in increasing the sophistication in music listening, and just to, as we say, the more we know about something, the more we appreciate it, and the more we can find ways of appreciating it. I want people to find more and more different ways of appreciating music, so that there can be more different ways of making music. One of the things that is wonderful about this huge industrialization and digitization of music is that it's so easy now to simply understand the ways that have been established of playing certain pieces of music. And it's very easy to copy. If you have good technical skills, it's very easy to just replicate that. But that is just one solution, or maybe a couple solutions, a couple ways of doing it. What if by having these tools and by seeing how similar things are, and then pushing and using that as an incentive to push ourselves to find other more creative solutions, we can come up with more imaginative ways of expressing music. I think that would be a much more interesting result.
So one thing you said earlier that I kind of want to go back to, and again, it's the idea that my job is sort of in social media and then in advocacy kind of would have been very hard for me to do 15 years ago. And your job, essentially, you've kind of invented your own career path. You've not taken a traditional academic career path at all, have you?
No, and it was not easy. I don't know that I would say to everyone, go out there and do this. It has not been easy to create an unusual career path, mainly because this particular field or the way in which I practice it tries to marry two rather disparate disciplines, music and mathematics and computation, and tries to integrate them very tightly. And many people, there have been people who have come before me, and primarily the way they have managed to carve out a path is by first establishing themselves in one discipline. And then once that path is established, to then branch out and do their own thing. I started out by saying, this is what I want to do, nothing else. And I want to combine music and mathematics and computation. And so when no such department existed, when I first began, finding a job took a little while. And it was a risky proposition. And even after I found a job, surviving the tenure process also took quite a bit of effort. But having said that, I feel incredibly fortunate to have found people who have been willing to believe in me and to allow me to do this. It's not easy, but I have been given a chance to do it. And for that, I'm extremely grateful. I am able to do what I love. And so every day is like waking up to a playground. It's I work incredibly hard, but it doesn't feel like work.
And what kind of qualities do you think are necessary to achieve what you've achieved in this sort of new field?
I would say persistence, but I wouldn't say sort of blind persistence. For me, I feel incredibly lucky that all the ducks lined up to allow me to do this. The field was at a point where it was ready to take off. Music technology was at a point where people were ready to accept it. I caught the wave at the beginning. And it's now much farther along, and so it's a more established field, but it's still kind of a niche field. I think that the advantages that we're now farther along is that it's no longer seen as completely outlandish to want to do this. There are degree programs in music technology. To succeed in this, one has to have something unique to offer at this juncture between music and technology. And because it's like the Wild West. It's hardly defined. It's hard to say what that unique thing is. And because there's no uniform training for this, everyone comes to this with their own background, with something that is different, or a different combination of skills. And so it takes probably finding a voice that is their own. And to be able to be very clear in defining what that is.
Again, I see sort of parallels with the sort of wider technology world where, there isn't a path to tread that someone else has so much done before you, because everything changes so quickly. You have to be pretty willing to readjust course on a regular basis and say, okay, well, that didn't work. We need to find a different way. And I think that flexibility has got to be equally as important, because I'm always been really interested in what happens at the boundaries between different fields, that when two areas overlap, I think that's always when something interesting happens. But it does take a lot of flexibility, I think.
Yes. It takes a lot of flexibility, and perhaps it takes underlying sort of structures to change. One of the things that I had to do over the course of my career was also to create the evaluation structures to allow my work to continue and for me to survive within the context in which I was in. And yes, the rules are not written. So because the rules are not written, you almost have to write them yourself. But I mean, not in a way that is unreasonable, but in a way that can be embraced and sort of set a path for others to also follow.
What is your next step? What is coming up for you that you're getting excited about?
I've been toying with the idea because I started my career in engineering schools, engineering departments, just because that was the departments that were more willing to embrace sort of an unusual application to music. And I'm interested whether now would be a time where music departments and music schools might be interested in these kinds of knowledge and in exploring how these technologies and methods can translate into the context of conservatoires and deep musical learning. I don't know how possible that is, but I'm willing to try. And it's because I think we have reached a point where it's only so much we can do with primarily technologists. We need to go where the heart, the core of the practice is. We need to go back to the music.
Well, thank you so much for talking to me. I could talk about this for a lot longer because I find it really fascinating. So thank you so much.
Thank you so much for having me.
You can watch Elaine's talk from Ada Lovelace Day 2015 at Conway Hall on our website. And we also have links to Elaine's 3 blogs. She has one about her music performances, one on her scientific research, and also a blog for the work that her lab is doing. So thank you very much, Elaine. And if you fancy playing us out with that same piece of music but played at the proper speed, that would be fantastic.
Okay, well, I'll go back to it. Thanks, Sue.
If you want to find out more about Elaine's work, we have a vast array of links in the show notes, including her 3 blogs, some of her research, and of course, video of her talk from Ada Lovelace Day Live 2015. Just visit findingada.com/ep9/. Our podcast is made possible thanks to the generous support of ARM, our exclusive semiconductor industry sponsor. You can find out more about ARM's energy-efficient microprocessor technology on their website at arm.com, and you can follow them on Twitter at ARM Holdings. If you'd like to join ARM as a co-sponsor of our podcast, then please get in touch. Just email me at Sue, that's SUW, at findingada.com. Now, the new year brings with it a whole new section to our podcast, Discovery of the Month, where we'll be exploring the story behind a discovery, breakthrough, or invention. This month, we're taking a look at a super strong plastic which, when it's spun into a fibre, is 8 times stronger than steel wire. It's used for making boats, bowstrings, cables, ropes, tyres, brake pads, helmets, walking boots, gloves, fighter jet wings, and Formula One car bodies and fuel tanks. It is most famous, though, for stopping bullets in their tracks. Yes, this month we're exploring the story of Kevlar, a material that is both ridiculously strong and incredibly lightweight. But why is Kevlar so strong? Well, like other plastics, Kevlar is a polymer, and the secret to its strength lies not just in the structure of its molecules, but also how they're spun into threads. Kevlar is a synthetic aromatic polyamide, or aramid, and its basic building block is a fairly simple monomer of hydrogen, carbon, nitrogen, and oxygen. This monomer is repeated many times to form long, thin, rod-like polymers, which are what you might call sticky. They line up with one another and form extra hydrogen bonds with their neighbours, sticking together. These polymers are then spun into a thread using a process called wet spinning. This makes sure that all the Kevlar molecules line up, increasing the thread strength even more. And finally, when those threads are woven into fabric, they become impenetrable. You can throw what you like at Kevlar, chances are it won't get through. Now, Kevlar's story starts in 1964 in America in the labs of the chemical giant DuPont. A chemist called Stephanie Kwolek was searching for a strong lightweight fibre to reinforce car tyres, helping make them more efficient. She was working with a polyamide solution that was behaving a little oddly. Normally, Kwolek would have expected a polymer solution to be clear or translucent and to be thick like molasses. This one was thin and runny, and it looked like buttermilk. Still, she persisted, curious to find out whether she could get anything useful out of this strange liquid. But when Quolek took it to the technician in charge of the spinneret, Charles Smullen, he did not want to try to spin thread from it. It was cloudy, and he thought there might be particles in it that would clog the nozzle. So Quolek filtered the solution to check and showed that no, it wasn't contaminated. Eventually, Smullen agreed to give it a go, and the results surprised everyone. The thread was lightweight and amazingly strong, and Quolek knew immediately that she'd hit gold. She experimented further and discovered that heat treating this new polymer made it even stronger. It's in this heat treatment that those important hydrogen bonds form between polymer molecules. And it turned out that Kevlar is resistant to wear, corrosion, and extremes of both heat and cold. The first Kevlar went on sale in 1971, and it's now mostly famous for its widespread use in body armour. Kevlar fabric is immensely strong enough to resist a knife blade or stop a bullet shot from point-blank range. Thousands of lives have been saved by Quolek's invention, and countless more people saved from injury. But the uses for Kevlar just keep on expanding. Motorola uses it to strengthen mobile phones. And if you like a bit of motorbike riding, you can now buy protective Kevlar jeans. You can even get Kevlar socks for those people who want to feel as if they're running barefoot but aren't so keen on lacerations. So the next time you want puncture-proof tyres, cut-resistant gloves, or a super strong mobile phone, say a little thank you to Stephanie Quolek. You can read more about Stephanie Quolek's life and work in Dr. Suze Kundu's chapter in our ebook, A Passion for Science, Stories of Discovery and Invention. It's available now on Amazon for just £1.99 or $2.49, and there's a link in the show notes to save you searching. So this month, I would like to welcome Dr. Helen Scales to the podcast. Helen was an Ada Lovelace Day Live speaker in 2012, and she is a marine biologist and writer. And Helen, you're going to talk to us about someone who's been quite a big influence on your career, correct?
Yes, that's absolutely right. So Eugenie Clark is a wonderful ichthyologist, a person who studies fish. And I was very taken by her really from a young age when I first read her books, and thought she was just wonderful what she did. And then actually a couple of years ago I got a chance to meet her, which was even better than I expected it to be, to meet her in person. They say don't meet your heroes, but it was absolutely fantastic. So, she's I guess I feel like she's sort of been there all the time, even though I only met her just a couple of years ago, that she definitely helped to spark some ideas in me when I was quite little, which was wonderful.
So can you tell us a little bit about what is Eugenie Clark famous for?
She's actually probably best remembered and kind of famous for being the Shark Lady. It was the title she was given, and that was a long time ago. It's probably back in the 60s and the 70s. I mean, she started out in the world of being a marine scientist, a fish biologist, actually even before people like Jacques Cousteau had begun to make the oceans very kind of sexy and appealing to people through his TV shows. And she was beginning to think about doing this kind of stuff around the time of William Beebe, who was an American adventurer and explorer, who I guess was a kind of predecessor to Cousteau, really. And he would go on adventures in the deep ocean and do some wonderful research. And I think he was quite a big inspiration for Jeannie when she was little. And, she was growing up in the 20s and 30s in New York. She kind of talks about kind of reading his work and thinking that maybe one day I could be his secretary or something. This, Dr. Beebe must need women in his life. She started out, I think, really as a female scientist at a time when that just wasn't very normal either, for women to kind of go off and do this kind of thing, and that's one reason why I really felt kind of drawn to Eugenie and what she did, because she clearly had this incredible passion for the oceans and for fish, but she also had to get across quite a few hurdles because she was a woman, but she didn't let that stop her. So that was for me, came through really strongly with everything that she did. But kind of dialing it back, when she was little, she says it was visits to the aquarium in Battery Park that got her really interested in fish in the first place, and her mum would take her down there, and I think eventually eventually she persuaded her mum to get her a fish tank. So she started keeping fish at home. So she was a bit of a Gerald Durrell and had all these pet fish, and then went on to study at New York University. She studied zoology and then went on to do a master's and a PhD. And definitely at that time, this wasn't very easy for her. It wasn't like there was easy funding available. She was definitely turned down at least once because for PhD funding, I think, because she was told, oh, she'll probably go off and have babies, so we don't want her around here. But she kept trying, and she did get more funding. She worked her way through quite a lot of her studies and did some really wonderful things. She did lots of really cool kind of experiments in the lab and studied, I think for her PhD, she studied these little fishes that are quite popular aquarium fish. And she was looking into how they interbreed and stuff, and she came up with some pretty cool stuff there. But then I think what really kind of grabbed me about her work and the stuff she then started to write about in her books was when she went off on expeditions and explorations around the world. And she just took off on her own. She was this female solo traveller and scientist, and was just incredibly pioneering in her bravery as well, really. She would sort of take any opportunity that came along to her, just to disappear off to exotic locations and follow her studies and get herself in the oceans whenever she could. And, she headed off to, she went island hopping around the Pacific and went hunting for toxic fish. She spent a year in the Red Sea. She got a Fulbright scholarship. And this was in sort of 1950, and she spent a year there, again carrying on her studies of the fish in the Red Sea, beautiful coral reef fish. And then she came back to America, I think in kind of 1951, and she'd written her first book, which is The Lady with a Spear, which is the first one I read, and that describes all these fantastic adventures she had. And it was picked up by a wealthy couple, the Vanderbilts, who they basically just thought this was wonderful what she was doing, and also that she'd worked in the Red Sea in this little research lab on the shores of the desert, and they wanted to set up something similar in Florida. So they brought her over. She gave a lecture, which she describes as being incredibly popular, that she didn't expect so many people to show up or be at all interested in what she had to say. And they were like absolutely packed out, and there were people hanging out the windows, like desperate to hear about these incredible fish that she'd studied in the Red Sea. So yeah, then in 1955, the Vanderbilts basically said, well, here's a bunch of money. We want you to set up your own research lab. So she did. She set up, it was originally called the Cape Hayes Marine Lab, and it was on the Gulf Coast of Florida. It's now become the Moat Marine Labs, which is a really big public aquarium. It's got a huge research institute attached to it. But it began as this little tiny, like one little room that they built with a deck and a dock next to it over the water. And it was just Jeannie and one other guy, basically this fisherman, who would go and find things for her and bring them back. And that's when her shark studies really began. That's how she got her name as the Shark Lady. She did loads of great pioneering stuff on sharks and sort of showing that they really aren't mindless killing machines, but that it could actually learn stuff. And she did loads of great stuff there. But she didn't actually stay at that research institute. She took up, in 1968, she moved up to Maryland and took up a position at the university there, and spent the rest of her career basically doing her research, like mentoring thousands of students and going off on great adventures and continuing her kind of explorations of the oceans. So she really did have this incredibly long life of just being this inspiring, just passionate lady. And it really came across to me, it comes across still to me in her writing. You get this feeling that she was so driven by finding new things out in the oceans. And she carried on right up to her death. It was amazing. She sadly passed away in 2015, and she was 92. And I think I met her just before that. So it would have been, I think she was in her very late 80s when we met. She was just a wonderful person. She was so lovely, just such a lovely person to meet. She was still diving. She went diving, I think, a few months before she died, carrying on her research. Like, she's had papers in review when she passed away. She was just so excited to find out new things and to keep pushing her science out there, that nothing stood in her way. And that was just, I found that so inspiring. I mean, it was obviously very, very sad that she passed away, but just her legacy and her energy, I think, is going to live on and on, really.
Curiosity doesn't retire, and she didn't retire. She just sort of carried on. I mean, it's so obvious that she really loved what she did. I mean, it was just a foundational part of who she was.
Absolutely. And that was so, I found it really infectious, just to see that in someone else. And I think, as I say, when I first read her books when I was a kid, at that point, I guess I didn't really quite know how much I was going to sort of follow that similar kind of route of wanting to be in the oceans, but I kind of had an inkling of it. And I guess seeing her at that point writing about what she'd done, and then, you know, it showed me that I could do it as well, and that there's no reason not to kind of sort of follow your dreams. And she totally did. I mean, she absolutely did. She just seemed to kind of grab life by the balls, really. I mean, she had 5 husbands, which I thought was rather good going, and 4 kids, and a lot of them would come on her expeditions with her. In fact, I was just the other day, for the book I'm currently writing, I was reading up some of the papers that she published just in those last few years when she, before she passed away, and there were sort of thank yous to her members of her family who'd come on diving expeditions with her as well, which I thought was rather wonderful. It was so lovely to meet her. I honestly was quite humbled, actually. I went to Moat Marine Labs, this lab that she originally set up, where she moved back actually in her retirement. She moved back there for the last 10 years and just kind of pottered on with her research. And I gave a lecture the night before about one of my books I'd written, and I was expecting to meet her the next day for lunch. We'd made a lunch date, and she showed up at my talk and stood in line waiting for me to sign my book for her. And it was just like, I've got one for you. I was going to give it to you tomorrow, but she was there just like, you know, everybody else, and seemed so excited to meet me almost as much as I was to meet her. And it was just lovely. It was so nice.
That is wonderful. And I mean, she's called the Shark Lady, but also wasn't she one of the first people to start using scuba diving in her work as a sort of research method?
That's right. Yeah. In fact, she kind of predates scuba as well. I mean, she's this one description in that first book of hers about going helmet diving. So that's when you've got a kind of big metal bucket on your head with a window in it and a tube going up to the surface, pushing with hopefully a compressor pushing air down to you at the bottom of the sea, and having a bit of trouble with that. And in fact, there was a sort of, I think the pipe came away a bit, and so she didn't have the air she needed and was nearly passing out, and then realised that she probably should swim to the surface. And then I think, again, this really reflects the kind of person she was. She then said, oh, well, I mean, I guess, yep, that was fine. I'll go straight back down again then, and not let this bother me and not kind of get put off this whole thing. So, yep, they fixed the kit. She put the helmet back on and went straight back down again. So she was really fearless. It was extraordinary. But yes, I think she did. She went on to do an enormous amount of underwater research with scuba, and also with deep sea submersibles. I think she went on something like 70 deep submersible dives and went down to something like 12,000 feet. I think she did it even into her 80s. She was getting inside these little submarines and scooting around in the deep ocean. And the funny thing was about Eugenie as well, like she didn't, even though she started off writing these books which were very popular, the rest of her career she wasn't this sort of big TV star. She isn't so well remembered as someone like Cousteau or various other kind of marine explorers. She just got on with it and did the work she wanted to do, and wasn't kind of seeking this sort of glory light of being this great explorer. She just wanted to do it, and that's why she did it. It wasn't for any other kind of, you know, famous reasons. She was very humble. It was amazing.
And so what do you think has been the impact of her work?
Well, I mean, winding back to this idea of her being the Shark Lady, and that is what she's very much remembered for. And she was a pioneer in that way, in that she wanted to show, I mean, she describes, I think, sharks as being misunderstood and magnificent. And I think she was really the first person to start to peel that back and say, look, you know, okay, things like the movie Jaws have given us this idea of sharks being, you know, terrifying, uncontrollable, just like bloodthirsty beasts. And Jeannie was one of the first people, I think really the first person who to start looking at that. And so, you know, they would catch sharks in the Gulf of Florida and bring them into the research lab, into the water next to it, in sort of water-based cages, and she would do studies, and she was the first person who ever taught a shark to respond to a target, which is kind of a common thing you would do in animal studies. You know, you can get other sorts of creatures to basically, with food rewards, get them to press a target of a certain colour or shape, and if they do the right one they get some food, and they learn that, and then they learn, okay, if I do this I get food, so I'll keep doing this. And sharks can absolutely do that, and they can remember things for quite a long time. When I met her, actually, I asked her, so, you know, how smart do you think sharks really are? Are they clever? And she's like, I mean, they're not as clever as dolphins, but maybe similar to some dogs, perhaps. She was like, they do have smarts. They're not hyper intelligent, but they're pretty good. And and there's a lot more nuance going on in these animals than anyone really suspected. So there are so many more studies now that have been done. More kind of is known than ever before about the shark brain and how it thinks and how it processes the world around them. But she was really the first one to start doing that and show that it was possible to look at them in this way. So, and I think it's a battle we're still pushing against, actually, to be honest. I think, there's still a huge misunderstanding of sharks. I constantly have family and friends saying to me, why do you go diving with sharks? Surely it's really dangerous. And it's like, well, no, there's maybe 2 species or 3 that you might want to steer clear of or be a bit careful, especially if they're somewhere where they're hunting, but the rest of them aren't. They're not interested in humans at all. They're hunters, just as there are tons of other animals that are hunters, and they're beautiful and interesting and fascinating creatures. And Jeannie, I think, was really one of the first people to kind of stand up and say that really loudly, and people listened to her, which was great.
Yeah, because I think we still have issues with things like Shark Week, where it's all kind of like, oh, look at the scary sharks, and that gets a little bit frustrating.
We've come a long way with Shark Week, but you're right, there's still a sensationalism about it. Even if it's like, oh, look at the scary sharks, but actually they're not so scary. But it's like, well, don't big them up, They are an immensely diverse group of animals. I mean, there's like 400 species. They're everything from something you could put in your hand to, great big great white sharks and everything in between. And there's so much more to them than just what they eat. It's like, can't we talk about all the other cool stuff, like the fact that 1 in 10 sharks can actually glow in the dark? I mean, that is cool. That's really cool. So
I did not know that.
There you go. so there's tons of stuff. Yeah, I think we still have to work pretty hard against that image of sharks, and they're not doing too well right now in their world. They are being caught in huge numbers, so I think now is more important than ever for us to actually care about them and try not let them all go the wrong way down the tubes. Yeah.
If people wanted to kind of have sort of one thing about Eugenie Clark that they should take away from this, what would that be?
Well, I think it has to go back to this, for me at least, who she was as a person and as a scientist, and just this immense passion that she had for all the amazing thing in the oceans. I mean, it doesn't necessarily have to connect to that. It doesn't just like, I think everyone should go and be a marine biologist, although I kind of do. But, it was just that she followed her passion and really pushed against adversity in some, in several occasions where being a woman just wasn't the easiest thing for her to do, but she didn't let that stop her. So I just, her books are wonderful. There's the 2 books she wrote early on, The Lady and the Spear and The Lady and the Sharks. And they describe her early work, and it, as well as insight into her as a person, they also give insight into the time that she was working, from the sort of 40s, 50s, 60s onwards, and what it was like to do science then, and the kind of things she was discovering. And she's just a really great communicator of science as well, and I know she carried on doing that and inspiring people all the way through her career. But her work, really, I think it's a great example of how to talk about science and how to make it interesting and accessible to a general audience. So, she was doing that way before tons of other people kind of jumped on that train. She was there doing this before Cousteau was doing it. So I think in that sense as well, it's a lovely thing to kind of get an insight into how to tap into that passion and communicate it to other people. So yeah, go read her book. See if you think I'm right.
Thank you, Helen. That was absolutely brilliant. Thank you.
Oh, it was lovely. Thank you for having me. I'm very happy always to talk about the oceans and to talk about Jeannie. She's a great lady and definitely needs to be well remembered.
For more about Helen's work, take a look at the links in the show notes, or you can visit her website at helenscales.com or follow her on Twitter at Helen Scales. Helen currently has 2 books out: Spirals in Time, The Secret Life and Curious Afterlife of Seashells, and Poseidon's Steed, The Story of Seahorses from Myth to Reality. Helen has generously given us a signed copy of Spirals in Time for a giveaway. All you need to do to take part is tell us on Twitter which is your favourite Ada Lovelace Day podcast episode. Remember to include our username, @FindingAda, in your tweet to make sure we see it. Get your entry in before the end of February and we'll choose a winner at the beginning of March, and we'll let them know on Twitter. Thanks again to our sponsor, ARM, for their ongoing support. If you'd like to join them as a podcast sponsor, please get in touch. Thanks also to our editor, Andrew Marks. Don't forget that you can subscribe to our podcast on iTunes, Google Play and Stitcher. And if you'd like to give us a little belated Christmas present, please do rate and review our podcast. iTunes especially is how people find new podcasts, and your review will really help them discover our work. It will take you just a couple of minutes, but it will really mean a lot to us. Next month, we're talking to software developer Ellen Gwynn, who's going to talk to us about how she made the transition from astrophysics to programming. And we've got theoretical physicist and broadcaster, Professor Jim Al-Khalili, who'll be telling us about Daphne Jackson, the first woman to become a professor of physics in the UK. So thank you for listening, and join us next month.